Hi, this is Mr. Whalen, and in this video I'd like to introduce a special number and concept that is fundamental to chemistry, the mole. Now when we talk about the mole in chemistry, we're not talking about a little animal that lives in the ground or a spot on your skin. A mole is a special number useful for counting atoms and talking about quantities of matter. So first I'd like you to recall a dozen. We all know that a dozen means 12 things. So when your mom sends you to the store and asks you to pick up a dozen eggs, what that means is pick up 12 eggs. Well, in chemistry, the mole works in just the same way. Consider this. I have a metal nut here, and as a chemist I might ask, how many atoms are in this sample of metal? And because atoms are so small, the answer is going to be a very, very large number. And even if I try to count with dozens, because a dozen is only 12 things, it's still going to be a very, very large number of dozens of atoms in this nut. So along comes the mole. For that reason, and more important ones that we'll talk about later, chemists came up with this huge number, 6.02 times 10 to the 23rd. And that is the number of representative particles that corresponds to 1 mole. Notice this is a huge number. If I were to carry out the decimal 23 places, I'd have 21 zeros following my 2 here, and it wouldn't fit on this page unless I wrote really, really small. Now I said before that the mole is used to count atoms. Well, that was only part of the truth. The mole is actually defined as this number of representative particles. Now what do I mean by representative particles? Representative particles can be atoms, molecules, or formula units. And this number is so important that it has been given a special name, Avogadro's number. So Avogadro's number is 6.02 times 10 to the 23rd, and that number is the number of representative particles, could be atoms, molecules, or formula units, in 1 mole. 1 mole is to representative particles as 1 dozen is to eggs. Dozen is used to count eggs. Mole is used to count representative particles, and this is what I mean by representative particles. Okay, now before we see this in action, I'd like you to notice that both of these equalities give us 2 possible conversion factors. 12 things is equal to 1 dozen. That means this is a possible conversion factor, and this is a possible conversion factor for the dozen, depending on what I'm trying to convert into what. Similarly, 6.02 times 10 to the 23rd representative particles is equal to 1 mole. I could use this conversion factor in my problem, or I could use this conversion factor in my problem. And we'll see how we figure that out in just a second. So first let's try it with a dozen. So for example, how many eggs are in 3 dozen? Well, I would start the problem this way. 3 dozen times some conversion factor. Now what's my conversion factor going to be? Remember, from unit conversion or dimension analysis, we want our dozen to cancel out. Notice if I use this conversion factor, my answer is going to be dozen squared over eggs. 3 over 12, dozen squared over eggs. That's not what I'm looking for. I'm looking for how many eggs are in this 3 dozen. So the conversion factor I want to use is there's 12 eggs per dozen. My dozen will cancel, and my answer will be 3 times 12 is 36, leaving me with 36 eggs is my answer. Now this is a really simple example. You probably could have done that in your head, but I wanted you to see that so that you realize it's the exact same thing with moles. Now look at this example. How many moles are in 1.806 times 10 to the 24th H2O molecules? I start out the problem in the exact same way. In this case, I have 1.806 times 10 to the 24th molecules. Molecules are my representative particle unit in this case. I'm going to multiply it by a conversion factor just like I did with dozen. I'm looking for the number of moles. I want to cancel out my representative particle unit. Notice if I use this conversion factor, I would get the wrong answer. I would get molecules squared over moles. But I'm looking for moles of H2O molecules. I want to use this conversion factor. 6.02 times 10 to the 23rd is my number of molecules per mole in this case. So my answer is going to be 1.806 times 10 to the 24th divided by 6.02 times 10 to the 23rd. My molecules will cancel. My answer will be in moles. And if we apply our rules for operations with scientific notation, we find 3 moles is our answer. So this huge number of water molecules is actually only 3 moles of H2O. And finally, how many carbon atoms are in 2 moles? Again, I start the problem out the same way I did the last two. 2 moles of carbon times some conversion factor. Well, which conversion factor am I going to use in this case? I hope you pick this one. Because remember, I want my moles to cancel. There are 6.02 times 10 to the 23rd representative particles in every mole of carbon. If I have 2 moles of carbon, multiplied by this conversion factor, my moles will cancel. My answer will be 2 times 6.02 times 10 to the 23rd representative particles, in this case atoms, giving me 12.04 times 10 to the 23rd atoms, which I put in the correct form when I move the decimal over one place. And that's how you count with the mole. In the next video, we'll talk about how this makes the periodic table so much more useful. I hope that was helpful.